yesterday we looked at stability of the control system, where we discussed about the poles and zeros for a transfer function. So this is the S-plane, and you can see the region of stability. Okay, so the poles should be on the left hand side of the plane. Okay, so only then the system is stable. If it's on the right side, it's the region of instability. Okay, so we discussed how to represent a pole on the S-plane. So it has the real axis and the imaginary axis. So the roots of the denominator is called as poles, and roots of the numerator is called zeros. So if you have the poles on the left side, it's the system is stable. If you have even one pole on the right side, that makes the system unstable. So what is stability? What is stability? Bounded input,
bounded input, output. Bounded output.
Okay, for a bounded input, we should always get bounded output. There should not be any unbounded output. Okay, for a small input, you should not get a very large output. Okay, that is the idea. So there must be the system must be stable, or sometimes the system is marginally stable. What is the situation where the system is marginally stable? The poles are located on the imaginary axis. Okay, there's no real term, only the imaginary term is there. So in that situation, the system is marginally stable. That is, it keeps fluctuating over a small range, but it doesn't go unstable. Okay, the output is not unbounded, but also it doesn't come to a steady state value. It keeps oscillating. So that is called as marginal stability. So we discussed about the poles, but what about zeros? Okay, so does zero affect the stability? Zeros doesn't affect the stability. Okay, so we'll look at the use of zeros or the role of zeros a little later. Okay, we'll concentrate only on the poles, because poles are the ones which is going to talk about the stability. Okay, so we'll do only with the poles for now. We'll discuss the zeros a little later. So suppose you have an input which is called as R of S, and then you have this comparator, and then you have the controller which is called as GC of S, and then you have the plant of the system, so you call that as G of S, and then this will have an output called as Y of S, and then you take a feedback from this, and then this is the sensor, so its transfer function is H of S, Okay, and then you connect this to the comparator, and here it would be minus and here it would be plus. So this way it goes. So this is how you represent a closed loop feedback system, negative feedback. So now if I have to get a transfer function for this, what do you mean by transfer function? I need to get y of s by r of s is how much? Okay, so y of s is the output, r of s is the input. Output by input is how much? So this is what we need to find here. So for this, if you see here, y of s is nothing but, I told you in S domain, we can, instead of doing the integration, we can do multiplication. Okay. So what it means is, so this is, I write it as E of S here, the error signal. Okay. This is the feedback which comes from here. This is the input. So the error is this E of S. So what is Y of S equal to? Y of S will be equal to Y of S will be equal to, it is the E of S multiplied by GC of S multiplied by G of S. Okay, so this error which is coming from here, and then this is the transfer function of this controller, and then there is a function of the system. So you can multiply all these three. Okay, that is the advantage that you get when you are doing it in the S domain. Okay, so Y of S is this. Now, what is E of S equal to? E of S is nothing but R of S, that is a input here, minus, it is H of S multiplied by Y of S. Okay, this is the output, gets multiplied here. This is the H of S here. So H of S into Y of S. So it is R of S minus H of S into Y of S. Okay, so this is E of S. Now I'll replace this term. So I can write Y of S as, how do I write Y of S now? Y of S can be written as GC of S multiplied by G of S, and then multiplied by R of S minus H of S multiplied by Y of S. Okay, so I open the bracket. Y of S can be written as GC of S, G of S, R of S minus GC of S, GS of S, H of S multiplied by Y of S. Okay, so this is, Y of S equal to, now what I'll do is I'll take Y of S here, I'll take Y of S here, Y of S, I'll take this term on the left hand side plus GC of S, G of S h of s, okay, this term multiplied by y of s is equal to this term here, gc of s, g of s multiplied by r of s. Okay, so this can be written as take y of s common. Y of s, if I take common, it will be 1 plus gc of s, g of s, h of s, and then is equal to gc of s, g of s multiplied by r of s. Okay, so what do we need? We need y of s by r of s. Okay, so we need y of s by r of s. So output by input, y of s is the output, r of s is the input. So what do we get? We get gc of s, g of s divided by 1 plus gc of s, g of s multiplied by h of s. Okay, so this is nothing but the transfer function for a closed loop system. Any doubts in this?
So this is this.
Yeah, tell me.
So at the EFS.
How to calculate
EFS. Yeah.
Yeah. See, E of s is nothing but this is the comparator. Okay, so this is the comparator. R of s is here. Okay, and h of s into y of s is here. Okay, this what you see over here. Over here comes the h of s into y of s. Okay, is it clear?
Yes, sir.
This is h of s into y of s here. So r of s minus h of s into y of s will give you E of s.
Okay.
Any other doubts in this? Any other doubts?
No, sir.
Understood
No,
this?
sir. No, sir. No doubt.
Yes, sir.
Okay. So what we have done is we have written just this y of s is equal to E of s into gc of s and g of s. Okay, and then I just wrote for E of s is equal to this thing, and then just the substitution part, and then you get this transfer function y of s by r of s. Okay, it's just the substitution to get the output by input. Now, what is h of s for a unity feedback system? For unity feedback, for unity feedback,
1, sir.
for unity feedback, h of s is equal to 1.
1.
Okay, h of s is equal to 1. So what will be the transfer function? It will be gc of s into g of s divided by 1 plus gc of s into g of s. Clear? If you consider h of s as 1. Unity feedback, that is you don't you assume that there is no noise picked up by the sensor. Okay, clear? So now we need to know whether this transfer function is giving stability. Okay, so stability of a system we need to check. So how do you check this stability of a closed loop system for a unity feedback? What will be the thing that you need to check? the denominators, right? 1 plus GC of S, G of S. Okay. The roots of this equation. The roots of this equation must be what?
Yeah. What is it? Negative, sir.
Negative. Okay. The roots, I have just taken H of S equal to 1. Okay. You know the poles must be negative for the system to be stable. Okay. So I'm just taking the denominator of this transfer function. Okay. 1 plus GC of S multiplied by G of S. This, the roots of this equation must be negative. Okay. Then only the system would be stable. Clear? Any doubts in this? Any doubts? Suppose, for example, I have an input R of S, and then a comparator here, and then I have a controller which is K, okay, and then this is 1 divided by S minus 1, okay, and then this is the output Y of S, and then I'll consider it as a unity feedback, and then connect this to this. Okay, this is negative and this is positive. Okay, so what will be the value of K? Is the system stable? 1 divided by S minus 1?
No, sir.
No. Okay, because the root is 1 there. Okay, positive. Now, what should be the value of K to make this system, stable? Okay, what is the value of K that makes the system stable? How do you find out? First, write down the transfer function. Transfer function is equal to, it was GC of S multiplied by G of S. Okay, if you see the formula here, this GC of S multiplied by G of S. Okay, so just write that. So what will this be? What will this be? Can anybody tell me? Do you want the diagram to be visible? Yeah, can you tell me what will be the numerator?
K divided by S minus 1, sir.
Okay, K divided by S minus 1.
Divided by 1 plus
There's a lot of background noise, Ritesh. Okay, K divided by S minus 1 divided by
Plus K divided by S minus 1.
1 plus
K divided by S minus 1.
1 plus K divided by S minus 1. So what will this be? What will this be?
K by S minus 1 plus.
So it will be, I'll take it as S minus 1 here. So it will be S minus 1 plus K. So this and this gets cancelled. It will be, transfer function will be what? It will be K divided by S minus 1 plus K. Okay, S minus 1 plus K. Now what will be the value, what should be the value of K to get negative poles. Yes.
Should be greater than 1, sir.
So K should be greater than
1.
K should be greater than 1 to make the system stable. Okay. Understood? So given an unstable system, you are using a controller that is a K there, and you are finding out the value of that K to make the system stable. Okay, so this is how you find the closed loop stability. Okay, in open loop, it was just 1 divided by s minus 1. Okay, so s will be equal to 1, so the system would be unstable. But when you're using a feedback controller, so this K, when you have some range within which the poles will be negative, then the system will be stable. Okay, so any doubts in this, the till now what we have done? Any questions? Did you understand the derivation part and then the finding the value of K to make the system stable?
Yes, sir.
So can you explain once more why K needs to be greater than 1?
Okay. Suppose if I put K less than 1, okay, K equal to 0. Okay, if K is 0, what will happen? S will be equal to 1, right? If I take the roots,
Yes, sir. Yes, sir.
S will be equal to 1.
Yeah.
So S will be equal to 1. The pole is on the right side of the S plane.
Okay. Okay.
Okay. We want to shift the pole to the left side.
Okay.
Okay. So for what value of K, the pole will be on the left side of this. Okay. Suppose if this is the S plane, the pole must be here. Okay. It must lie on the left side of the plane. Okay. Only then the system would be stable.
Okay.
So for what value does that is the value of K makes the system stable? That is the question.
So we
what?
need S to be negative, is it?
Yeah.
Okay. Okay, sir.
S minus 1 plus K equal to 0.
Yeah, I got it, sir. I got it, sir.
Okay. Any questions? Any doubts in this? Any doubts?
No, sir.
So here I have 1 divided by S minus 1 first. So I'll just run this. Then go to the apps, linear system analyzer. And then take the plot configurations. I want to see the impulse and then the pole 0. Apply this. Say OK. and then import the file, this transfer function. So you can see the pole is at 1 now. So the system is unstable. So what you do, k divided by s minus 1 plus k. K should be greater than 1. Say I put it as 2. Okay, 2 divided by s minus 1 plus 2. Okay, so just run this and then refresh. The system becomes stable. Okay, so system becomes stable here. Now this is the value of k greater than 1. Whatever value we put greater than 1 will have the system stable. So we need to make the system stable, and for that we need to determine the value of k. So if this is the simpler equation, so it was easy to find the value of k. But if you have a polynomial, say cubic polynomial in the denominator, then finding out the value of k would become difficult. So there are methods to find out the value of k to make the system stable. So did you understand the closed loop control system? The why that k is there? What is the system? Have we considered disturbance here?
No, sir.
We have not considered disturbance yet. Okay. And we have also considered it as unity feedback. Okay, so we have considered it as unity feedback. We have not taken into account the disturbances. Okay, so without these, just taken a system, we found that it is unstable. So we found what should be the value of k to make that system stable. Clear? Any doubts in this? So suppose if you have a I'll just show you this s plus 1 in the numerator divided by s minus 1 in the denominator. So you have a 0 now. So what is the value of 0? S is equal to s plus 1 divided by s minus 1. What is the value of 0? I want some response. Hello? What is the value of 0 here?
0 will be -1, sir.
-1, sir.
Yeah, 0 will be at -1. So we'll refresh this. Can you see a 0 at -1 here?
Sir.
Okay, so pole is represented by a cross and 0 is put as 0. Okay, this is called as pole 0 map, and in this 0 is represented with a 0 symbol 0, and this pole is represented as a cross here. Okay, so suppose if this was s plus 2, say, okay, I'll refresh this. Now the system is stable. Okay, the system is stable, but even though this is I'll put it as -1 here. Okay, so what you see here is s is equal to, you have a pole at -2. Okay, s is equal to -2, you have a pole, and then you have a 0 at 1. Okay, you have a 0 at 1. Now even though the 0 is on the right side of this S plane, the system is not going to unstable. Okay, so the stability is going to be determined only by the poles, not by the zeros. Okay, stability, whether the system is stable or unstable, we're going to define only based on the poles, not based on zeros. Okay, so this is a very important point you need to understand. So zeros are not going to make the system unstable, but poles can make the system unstable. Okay, so this is very important. And always remember, these transfer functions are nothing but related to the physical systems, real systems. Okay, you do a mathematical model, get the transfer function, and then make a controller for it. So this is how it has to be understood. Don't consider it as just an equation and you're trying to find the poles and roots, poles and zeros. Okay, so understand that the transfer function, we have done it for the hair dryer. We did the system identification. So we identified the system with a mathematical model. So whatever equations, whatever transfer functions we use, you must understand that this transfer function relates to some physical system. Okay, so that is very important. If you don't relate to the physical system, real systems, it becomes difficult to understand the concept here. Okay, so please relate these things to the physical system and then understand what a pole zero map is. Zeros, how you identify, how do you identify the poles? So how do you find the roots of this? Who is that? Okay, so any questions? Any questions so far?
No, sir, no question.
Okay, so I have uploaded some material in the Google Classroom now, and then I keep updating the uh, folder. Okay, Google Classroom, please go through those videos, and so that the topics are revised. Okay, so in the next class we will talk about how to find the value of k when the equations are much more complex, like um, s to the power of 4 or s to the power of 3. The cubic equations are there. How to find the value of k there? Okay, using MATLAB it would be easier, but if you have to do with pen and paper, then finding the value of k would be difficult. So there are some methods by which you can solve for k and get the value of k to make the system stable. So you have understood these transfer functions, the closed loop transfer function. This derivation is very important. The I don't think this derivation which I did for the closed loop transfer function is very important. Make sure you understand this, how to derive this. Okay, and this will help a lot in the further classes. Okay, so make sure you have understood this particular derivation. Any doubts on this?
No, sir.
No, sir, no doubt.
Okay. Hmm. Can somebody explain me what is a transfer function? Can someone explain what is transfer function instead of just output by input? Can you explain a little more on the transfer function? No one?
There's an impulse response of an when initial conditions of the systems is 0, sir.
Did you use the term Laplace transform?
Yes, sir. Laplace? No, sir. I didn't use the term Laplace transform. I
Okay.
just
It
Sir,
is the,
the transfer function will predict the output based on the input.
yeah, but it is in S domain, okay, of the impulse response. Okay, Laplace, the transfer function is always for the impulse response. Okay, and it will be in S domain, which is nothing but the output by input. So that is to be remembered, the transfer function concept, and how we are multiplying this GC of S and G of S. So this multiplication is possible only in S domain. It's not possible to multiply these in the time domain. Okay, so multiplication, we are writing y of s is equal to e of s into gc of s into g of s. This is possible only when you write this in S domain. Okay, otherwise it will be a integration in the time domain. So this is the advantage that you get when you write in S domain instead of the time domain. That is why we use all these techniques for the controlling in the S domain, and also look at the time domain for our better understanding purposes. Okay, so make sure you know the advantage of why we are using S domain here. Otherwise, the time domain is much simpler, but for design of the controller, the S domain is easier. The use of S domain is easier. That's why we use S domain. Okay, and the feedback, we take it as unity feedback to keep it simpler. Okay, otherwise, if the sensor picks up some noise, then h of s is not equal to 1. Okay, so it will also have some value. So h of s will not be equal to 1 if there is some noise to be considered. Then we have not added the disturbance to this yet. We'll add that later. And zeros doesn't affect the stability. The poles determine whether the system is stable or unstable or marginally stable. So these are some points you need to understand. So I think we'll stop it here. Any questions? Okay. Please try to respond as much as possible in these online classes. If you keep quiet, then I don't know if you're learning. Probably we'll have some questions from the next class so that you answer those. Okay, so we'll do something for your attentiveness. Okay, thank you. Bye.
Thank you, sir.
Thank you, sir. Thank you.
Thank you.